All righty. I'm not sure where a couple people are. Some are. I still need to get a quiz 5 to you. I realize you might say don't rush, but yeah, I need to get that to you. Trying to get that done. But we've opened up Module 6, which is Chapter 5. And I think to begin this, actually, let's go back to this basic question of dependence. Okay, so, right, definitely since Chapter 3, we're just looking at this basic question of dependence or independence. Okay, between two variables. And so every single time we do this, we're asking this same question, okay? And so, you know, for instance, what's something that might be on our minds these days for our two variables? Well, it might have something to do with vaccines and disease, COVID-19, for instance. You know, the question of dependence there, very important, right? I manufacture a vaccine, and the question kind of becomes, right, one variable would be the status of a person's vaccination, right? I've either been vaccinated or I haven't been vaccinated. So there's my explanatory variable. And then the response would be, you know, sometime down the road, did I ever get a particular disease? So, for instance, COVID-19. And again, well, you know, I did or I didn't. Or it might even be in gradations kinds of things. You know, I did, but, well, it wasn't too bad. Or I did, and it was horrible. Or something like that. And, you know, there, we hope there's a dependency, right? Is that if I know, you know, if I'm manufacturing a vaccine for health and I know a person has gotten the vaccine, I certainly would like to be able to say, oh, they are less likely to get sick. You know, and so you see, you've changed your prediction about a person and the disease based on information on the vaccine. You know, that's what we would hope. And so, you know, there's a place where we are absolutely hoping, and, you know, we would also hope that it, you know, it doesn't go on the market, so to speak, unless they have shown that it's dependent. Right? I mean, the last thing I need to do is go get a vaccine that doesn't do anything, right? That's actually independent of the disease I'm trying to ward off. And so that would just be horrible, right? You know, so we assume that if we go get a vaccine, this type of study has been done, and there is a very nice dependency. Okay, more than just, oh, well, you know, it just barely made it under that 0.05 mark, and, you know, I mean, we hope there's really a difference, you know, there's, and then, you know, and of course we do get into statistical versus practical. So if you have enough trials, you could show a difference of, oh, you know, without the vaccine, 80% of the people who get exposed get sick. And with the vaccine, 79% of the people who get exposed get sick. Well, you might be able to say that there's a statistical difference, but I, at that point, wouldn't be too worried about getting the vaccine. right? It would have a practical consideration as well. But we hope there's a dependency there. Now, on the other hand, my mother-in-law, she used to, so this was, gosh, when did they stop sending up space shuttles? Do you people ever remember watching a space shuttle launch or anything like that? Yeah, it's been a long time. So, go back a long time. Space shuttles. Shuttle launch.
The last one was July 8th.
Isn't Google great? When? Yeah. 2007?
2011.
Oh, 2011. So not too bad. Less than 10 years. So, my mother-in-law, she insisted that every time they launched a space shuttle, it was terrible weather in Grand Rapids, Michigan. Now, for those of you who know your geography, at least somewhat, they're pretty far away, right? They're launching in Florida and Grand Rapids. That's probably, I'm guessing about 1,400 miles, something like that. But she insisted that happened. Every time there was a shuttle launch, terrible weather in Grand Rapids. Now, my guess is that if you actually look, you would find these are independent. Oops. Right? Whether or not they launch a shuttle in Florida really has very little to do with the Grand Rapids weather. Now, that said, on the other hand, it did occur to me that with weather patterns, right, when do you launch a space shuttle? When it's nice in Florida. When is it nice in Florida? Oh, well, actually, it might be more likely to not be so nice in Michigan. Now, she was looking at it as cause and effect. In other words, that rocket went up, that caused it to rain or something like that in Grand Rapids. So, not just dependency, she was looking at causation. But most likely, nothing to do with each other, right? And part of it, too, was, well, she heard about space shuttle launches, but all the other launches, she never heard anything. She didn't hear about a satellite going up or something like that. And so, most likely, if I know they launched a satellite today, I'm probably not going to go, oh, it must be raining in Grand Rapids, right? But that would have been her feeling. Okay, nothing there. They're independent, most likely. Again, I say most likely. I never checked. Okay, mostly because she was not really worried about dependence or independence. She was sure it was a cause. Okay, so yeah, that's not much I could ever say there. We have things that are independent, and that is that knowing something about one doesn't tell me anything about the other. And certainly it doesn't go the other, if I know the weather's good in Grand Rapids, I don't immediately say, oh, they must not have launched a satellite or something, or if the weather's bad, I don't say, oh, they must have launched a satellite today or something. No, that's not going to happen, right? So we've got dependence, or at least we hope there is, and then independence and stuff. Okay. So now, I'm going to go ahead and just get rid of this, though. So as we've looked at this question, and again, this is all we want to know. We want to know, does knowing something about one variable help me to know something about another variable. We have done 2 chapters so far and into a third. And again, if this is our response variable, put that in there, response. And then the type of variable we have, so we could have a categorical, we could have a numerical. Here we could have categorical, and this would be our explanatory. And we could have numerical. Okay, as we looked at this question, it's just been a matter of how are the data coming in. So first we were in chapter 3, and we had categorical explanatory variable, categorical response variable, and so with that type of data, we used a chi-square test to determine a p-value. And we'll get to the p-value in a second. Then we moved to chapter 4, where we had a numerical response, but a categorical explanatory variable. So again, the big one is just like, well, different fertilizers for some sort of crop. Okay, you'd probably measure the crop in bushels per acre, something like that. But the categories would be fertilizer A, fertilizer B, maybe no fertilizer, something like that. And with that, we had to move to an ANOVA, an analysis of variance. But that particular test produced a nice p-value for us. Now we're in chapter 5, and we're using linear regression. And we have 2 numerical variables. And so we'll use this. Now, we won't do much at all with this up here. Mostly because we just don't have any easy software to do it. And so we'll talk about it a little bit, but not much to do there. And actually the textbook, a part of chapter 6 goes here, but then actually the big part of chapter 6 kind of goes with what do you do when you've got a mixture of all sorts of different variables because of confounding and all that. Okay, so we have that, so we want to begin looking at linear regression, but again, first, all these tests, every single one of them, it comes down to, in very general terms, we've got a null hypothesis, and every single time, however we state that null hypothesis, it doesn't really matter how we state it. In a very general terms, it comes down to the 2 variables are independent. Every single time. So if we end up failing to reject the null hypothesis, we end up saying, well, we don't have enough data or enough evidence to say these variables are dependent. Okay, so, do we know they're independent? No. But we don't have enough evidence to say they're not independent. And so then our alternative is that the 2 variables are dependent. Okay, and I mentioned p-value. Every single time we get data and we use one of these tests with our data, we throw it in, we get an answer out. That answer is called a p-value. And that p-value here, we end up getting stuck with our null hypothesis, and that is a good way to put it most of the time. We got stuck with it. We didn't get to get rid of it. Okay, because usually that's what we want to do. Again, think of the vaccines, right? I want to get rid of the hypothesis of independence. I want that to not be true most of the time. Because I am, the only reason I'm analyzing these two variables is because I think they have something to do with each other. Oh, dependency. And so we get this p-value, and if it's big, as in bigger than 0.05 for us most of the time, then yeah, we're stuck up here. And if it's small, less than 0.05, then we get to go with that alternate hypothesis. We get to say, oh yeah, these two variables are dependent. Okay, and back here at chi-square, it was independent or dependent, right? We had the chi-square test of independence. That was the whole name of it for two variables. So, independence or dependence. Now, it also had to do with the proportions, so you could go with, all the relative proportions matched each other across rows or across columns. That was the null hypothesis. Or, the dependency part was, there was something different in the rows or columns with these proportions. Then chapter 4, you could say, there's a dependency or it's independent. Well, independent was all the means were the same. Right? So specifically for that one, it was all the means are the same. So this was proportions, this was means, and then the alternate was at least one of the means was different. Okay? Well, why the difference? Well, different type of data. Here we had count data, so we could look at proportions. Here we have numerical data, or at least the response is numerical. And so we could take averages. We could look at means. And so now, as we go into chapter 5, everything's numerical. And so what will we look at there? Well, we'll see that in a second. Now, the p-value. So that's what we look up as the p-value. And part of the reason I'm going through this, right, is I just, I got back your project 3s and 4s, and that's where you really start using this stuff and talking about it and trying to put it in your own words. And there are some real misunderstandings, right? Or at least possibly not even going as far as misunderstanding, but just, you get the basic idea, but you've got these two things switched. Okay, well, when it comes down to it, that's either a misunderstanding or just a lack of understanding. You never knew to begin with, so there wasn't anything to misunderstand. You just didn't understand. But this makes a lot of sense. Why we would do this, and again, it's okay. What is a p-value? Okay, for the p-value, every single time, again, this doesn't change. Now, the tests change. The test statistics, the type of data, all that changes. But this never changes. This never changes. If H0 is true, okay, and it always starts there. Your p-value is based on the null hypothesis. It says, okay, we are going to assume this is true and run a bunch of experiments. That's what we did in Chapter 2. That was the idea of Chapter 2, was to get you this feeling of running a bunch of experiments. Not like 5, but 1,000 or 10,000 or 100,000 experiments, and asking, okay, if in every experiment we make sure H0 is true, and then throw out this random data based on H0, based on that assumption, let's look at the data we get. And so, if H0 is true, then this p-value is, so it's, if H0 is true, the p-value, well, I don't want to write it that way, the probability of getting our data. Okay, now I'd love to be able to just stop there, but it's not quite that. Okay, it's, I think, a reasonable intuitive idea. It's, if H0 is true, then the probability of getting our data, and that would come from, all those times of trying. Well, except you got to be careful, because as soon as you start talking about numerical data, so Chapter 4 had numerical data, Chapter 5 has numerical data. Well, actually, the probability of getting a single type, a kind of response for your data is always 0. Okay, because there's an infinite number of possibilities. So to go, oh, yeah, what's the probability I get an average of 4.32? Well, it's 0, actually. Okay, if you're dealing with a continuum and numerical data and so on, it's going to be 0. Okay, so to just stop there and say, oh, the probability of getting our data, not, so we have to put in an or data that are more dependent. Now, and I chose to go with more dependent to go with our idea of H0 and HA. So what we're looking at when we look at this is, we've got this null hypothesis, an alternative hypothesis, we get our data. Now, if the data exactly were to match the null hypothesis, well, then I'm done. Right? If I created a chart, a table that had perfectly independent rows and columns from just randomly getting data, well, I'm certainly not going to show they're dependent because they're perfectly independent. But generally, that's not going to happen when you collect data. Right? If I collect 2 sets of data and check their averages, they're likely not going to be the same. Again, if we're talking continuums and real random sampling and all that. Okay? So we're looking at this probability of getting our data, or something that's even more dependent looking, farther away from the null hypothesis. I should probably put the probability, I guess. The probability of getting our data or data that are more dependent is the p-value. And that's all it is. That's all it ever is. And so when you look at this and you say, oh, okay, so I'm assuming this is true, and I look at my data, and the probability of getting that data, or something actually more dependent than that, going with the fact that that's true, if that probability is kind of big, oh, well then, sure, why shouldn't that be true? right? If my hypothesis is that I have a sack containing all red marbles, and you pull out a red marble, well, okay, I believe you, right? Because the probability of pulling out a red marble, or any other color worse than that, well, is pretty much 1 if I assume I've got a red marble in there, right? 100% chance of pulling it, So of course, if I pull out a red marble, I'm going to go, sure. And so if that probability is high, now it's rarely going to be 100%, but if that probability is high, 20% chance, we're going to say, well, we don't have enough evidence to say it's not. Okay, but if I tell you I've got a bag of red marbles, all red marbles, and I pull out a green one, well, when you think about what's the probability, if all the marbles are red, the probability of pulling out a green one is 0. And so if I pull out a green one, do I believe that that bag has all red marbles? No. Now, that's an extreme case, but that's the idea, right? If I get data that it just seems so unlikely that that data came from that hypothesis, if it seems so unlikely, now again, 1 in 20 is not that unlikely, but it's what we use. But if it seems that unlikely, then I'm just going to have to say, no, I just can't believe that's true. That must be what's going on. Okay, and you just take some extreme examples like assume all red marbles, pull out a green one. I am no longer going to believe it's all red marbles. Right? Well, why? I mean, think about why. Well, because the probability of pulling out a green one from all red is 0. It's tiny. Okay, so tiny p-values go with the alternative. Big p-values means we can't go with the alternative. We're stuck with the null. And so we don't have enough evidence to go with the alternative. Okay, questions on that? Anything? Okay. Now, so, kind of using the chart idea again here, we'll kind of look at the different chapters and look, I'll call it graphically, but when you have tabular data for chi-squares count data, it's kind of hard to really call it graphically. It's visual, I guess. And so, when we were looking at the chi-square, and we'll just go with something with a couple categories in each variable. And to make them variables, they do need to have more than one category, more than one possible value, because then they aren't, if they don't, they aren't a variable. Right? If I say to my grandson, hey, that's great, go put your green shoes on, and all he's got is one pair of green shoes, well, he didn't really have a choice, right? There's not a variable in the shoe type or something like that. So with the chi-square, we might have variable 1 and a couple categories, A and B. Variable 2, a couple categories, C and D. And suppose that count data were something like 10 and 20 and 30 and 60. And as I look at that, you see, when we saw something like that, I went, independent. And again, what you want is a feel for just kind of looking at something and saying, well, why would that be independent? Well, look, if you tell me I'm in row A, I'm going to predict that there are twice as many D as C. Make sense? Right? If you tell me I'm in row A, I'm going to predict there are twice as many D as C. Now, oh, you give me new information. No, actually you're in row B. I'm still going to predict twice as many D as C. My prediction didn't change. I got no new information really by knowing which row I was in. Didn't help me a bit. Or you could go with columns again, you know, this is 10 out of 40, this is 20 out of 80. Proportions are the same, 1/4. And so, you know, in this case, if you told me I was in column C, I'd go, oh, A happens 1/4 of the time. Okay, you tell me I'm in column D, I'll say, oh, A happens 1/4 of the time. Nothing's changed. It's independent. I got nothing out of it. But, on the other hand, with that chi-square, if we go to, you know, change it just slightly, go with 20, 10, 30, and 60, A and B. Now, oops. E1, E2. Again, you know, this was our chapter 3 chi-square type of data. But I look at that, and now, all of a sudden, maybe there's a dependency. I don't really know till I run the test and get my p-value. But there might be a dependency because as I look at this, C and D, if you tell me I'm in column C, I'm going to say, oh yeah, well, yeah, 20 out of 50 chance of being in row A here. 20 out of 50. A little less than half. So if I needed to predict, was it going to be A or B, and you told me I was in column C, well, I'd predict B. More there. Now, if we move over to column D, in a way, you got to, you know, this is where you have to be a little careful is, well, you know, would I still pick B? Sure. B still outnumbers A, but look at the difference. You know, here it was 40%, 60%. Okay? 2 to 3. Doing a little better by picking B, but not way better. But boy, you tell me I'm in column D, I'm going to pick B and feel good about it. Right? Because, well, 60 to 10, 6 times as likely to get a B than an A. It matters, right? All of a sudden, even though in both cases I'd pick B, but, you know, say I was, I don't know, it was like putting money in the stock market or something like that, I would risk a lot more if I knew I was here in D than I would if I was in C. I would change my prediction. Not necessarily in what I thought was the most likely thing to happen, but how likely that was, right? You know, here, 60 to 10 or 6 to 1, here just 3 to 2. Okay? So if I was betting on the outcome, I would much rather know I was in column D. And then if you go the other way, if you think of the rows, well, then things really do change, right? If I tell you I'm in row A, well, then the most prevalent thing is C. If I tell you I'm in row B, well, the most prevalent thing is in D. That very much changes, right? The winner, so to speak, changes in that case. And so this, very dependent. Now, I say very depend, I mean, I still need a p-value to know, because, yeah, it may turn out that I can't truly claim this because the p-value is too big. Okay, but the idea is that looks like a dependency, that looks like it's heading toward the alternative, that looks like it's the null, the independence. And then, if we go to a graphical picture of an ANOVA, well, usually because we have numerical data for one variable and categorical variable for the other, probably box plots are in order. And here's category A, B, and C, and here's my response variable going up and down numerically. And I look at that, and it looks to me like it's independent, right? If I, as I just look at the data, so this would be something we might use with an ANOVA, and, this looks independent. Because again, it doesn't matter. I don't care what column I'm in. I get the same data. All looks the same. Okay, same average, and that's actually what it tests. It all looks like it's about the same average. But if you had something that looked like this, for your box plots. So this was A, B, and C. Well, it definitely looks like something matters here. Right? I don't know if I want to be higher or lower. I probably don't want to be in between, but who knows? Maybe I do. Maybe I want to be in the middle territory. Again, if you talk stock market and risk, well, it could be that you're looking at risk and you want some medium risk or something like that. And so you go, oh, well, yeah, we'll go with that. Okay, but that, definitely as I look at that, there seems to be a trend as I go down. Now you got to be careful with categorical because you really shouldn't call that a trend. I mentioned that, but I should probably wash my mouth out with soap or something for saying that. Right, because I can mix these categories up any way I want. So I can make these look like they're going up, and they're just categories. Doesn't really matter. Okay, I could make them look like they kind of, the high one could be in the middle, so they sort of went up and then back down. Okay, and it may not matter whatsoever as far as those categories. Maybe these are colors. Aqua, blue, and it's a C color. Pink? No. Oh, the C is silent. I said, what's a C color? C.
Oh,
Yeah.
I thought you meant like
Yeah. Cyan! There you go. Yeah, actually, we should think about that. I mean, that should be on the tips of all of our tongues, right? Because computers and all that, right? So, but those could just be colors. So who cares what order I put them, right? It doesn't matter. But I can still see that, oh, that's the lowest, that's the highest, that one's in the middle. And so this, again, some sort of ANOVA, looks like. But this, I would guess, might turn out to be dependent. Again, without the p-value, I really don't know. But that's the picture I'm looking for. Something where those box plots do not line up. And then finally now to chapter 5 with our regression. What we see there is, we'll have an X and a Y. This is typically explanatory or called a predictor. We tend to mention the word prediction a lot more when we start talking least squares and regression. And here's our response. But, for something that's independent, again, the idea is, and you can kind of use the box plots as a guide, is, why wasn't the box plots look independent? Well, because as I looked across, nothing looked different. Oh. Well, here, as I look across, nothing looks different. So, if I were to pick an X there, I would guess something in there looks a lot like a box plot kind of thing. If I picked an X way up here, I would still guess something in there. This looks independent. Okay, because knowing that I'm here with X or knowing that I'm there with X, it really doesn't change my view of what's going to happen. Right? Same thing. Doesn't seem to matter. Now, on the other hand, if my data are going up like this, so there's my X and my Y. Now, if I'm down here, oh, well, it looks like from my data I should guess something in there. Okay, that's the prediction idea. But if I'm up here on X, I should guess something way up there on Y. Oh, yeah, I changed my prediction. I changed what I thought was going to happen. Oh, dependent. Okay, and again, as you look at things in chapter 3, right, I erased the table, but what could we see? We could see proportions. That's visually kind of what you could see. You could see proportions of things, relative proportions. Here, visually, what do I see? Well, given that I have the whole box plot, I can see quite a bit, but the main thing that actually we tend to be looking for is I can see the averages. Now, these are probably really medians, but they're close to the average. But I can see that the averages or the means look like they're very different. Here they look to be the same. So here, what am I looking at? Well, here I'm really looking at the slope. And so here the slope looks to be 0, and here the slope looks to be not 0. And sure enough, that's what we look at. So with linear regression, in some ways, we are really limited. Okay, so in some ways. Now, so I'm going to say that we are. So linear regression, limited. Okay, so it's limited to looking at dependence or independence. So dependence based on a straight line model. Okay, so see, something like this is great. That's fantastic. But unfortunately, if I have data that actually I know fits a cubic. So here's a cubic, maybe something like that. So I know my data fit that curve exactly. Okay, I can't get more dependent than that. Right? Definitely if I know the formula, right? If you tell me an x value, I'll tell you the y value. I'll put it in a formula for the cubic, and I'll tell you what it is. That's dependency right there. I mean, I can tell you exactly, not just, oh, I'm going to change my prediction to, oh, high versus low or something like that. No, you give me an x value, I will tell you exactly what the y value is. A lot of dependency there. However, most likely, this would, something close to this, and we'll see a Desmos example in a minute with a quadratic. Something like this would probably tell you independent. Okay, why? Because it's basing it on a straight line, right? So this would probably come out to be independent. But if you had similar size data or whatever, and it was pretty spread out, but you noticed just at least a slight downward trend like that, then that data you would probably find to be dependent. Yet, I might not be able to predict nearly as well from these data here that it says are dependent compared to what I could predict for what it would say is independent. That's a limitation. That's a problem. Okay? Now, as it turns out, it's a problem we can get around. We can trick it and get around this problem. And actually then make it extremely flexible. It's fantastic. But so, kind of expanding on this, how do we trick it? Well, the way we're tricking it is that linear regression, now this is kind of the first time we're really talking about a model, okay? So a mathematical model, a formula kind of thing. Linear regression assumes, so this is part of the H0, okay? It's looking toward this model, y, and now when you're talking about modeling and statistics and random variables and explanation of one random variable by another with a model, you tend to use a tilde. I have a quick question for you. Is that a tilde or a twiddles? You don't know? You've never heard either one? Oh, I was just checking so my PhD advisor was from Scotland. And well, in Scotland, that is a twiddles. So I wonder if maybe South Africa maybe might be a twiddles as well, but we'll still not know. Maybe that could be a homework assignment for you. We call it a tilde, and we'll have bx plus a. So this looks a little weird for some of you because you usually are seeing mx plus b. But again, in statistics, they tend to use a b or a Greek letter beta for the slope here, and then an a or a Greek letter alpha for the y-intercept. And so this is what they base it on, and pretty much the way it works with this model is we start with a really simplistic model. I mean, you can think of it this way. And so, here's x, here's y, here's a bunch of data. About as simple a model as I could get for x predicting y would be, just take the average, which is probably in here somewhere, y bar, take that average, that sample average, and assume a constant. That's the simplest prediction I could probably come up with. Now, if I want a particular x value to go with that, well, why not x bar, and kind of. Now, there's no reason I really have to have that, but here's the interesting thing, is that our model that this is based on, the one that they spit out with this slope, it always goes through that point. And so that's where you can really see what the dependency is. When we use this model, it is always going through this point, and then the question just is, should that line be tipped like that, to best explain it, or, should it be more flat like the constant y bar? Okay, and that's the idea of the slope, and that's why, the null hypothesis is, well, if there's no dependency, then b equals 0, but the alternative is that b is not 0. And so when you get a p-value, it is the probability that you could get whatever slope we get out of this, which probably won't be exactly 0, almost never is. But it's the probability you could get whatever slope we get from this model if, in reality, the slope should be 0. Right? The data are coming from something where the slope should be 0. So the p-value is just looking at that probability of getting the particular slope that we got. Or something steeper, because that would be farther away from 0, a slope of 0. Okay. Wow. So, I kind of do the same thing on each day, because that's kind of the way it turned out people voted for. I didn't get as far. I thought I'd get further. Silly me. But anyway, so I didn't get to show you the Desmos thing. I'll try to put that in a video. Now, you can always, once I get it all uploaded, you can always go back and look at Tuesday's class if you want as well, for more information. But I'll try to add that video to the Blackboard. Okie doke. Well, I will see you next Thursday then.